All right, so here we have to set up an ice table because we have the starting concentration of the reactant, NO2, and we got the equilibrium constant, right? And so first thing you want to do is you want to convert the moles and the volume into molarity. So 0.5 moles divided by 2 liters, and that should give you 0.25 molarity for your NO2, okay? So you're going to be starting with 0.25 molarity of NO2, and it doesn't seem like we have anything else for the product, so we're going to assume that we start with just a reactant, okay? Now we got to figure out the change. Now we have to keep in mind the mole ratios between the two. So since we only start with reactant, we have to lose some of the reactant, right? So we're going to do minus 2x. Here it's going to be plus 2x, and it's going to be plus x, okay? So we got 0.25 minus 2x at equilibrium, 2x at equilibrium, and we got x right here, okay? So far, so good? Alrighty, so what we want to do now is we want to set up our equilibrium constant equation. So K is going to equal the concentration of the products to the power of the mole ratio, so power of 2 for NO. And then we got the concentration of O2 divided by the concentration of NO2 and squared. Okay. All right, so if we just plug in our values, it tells us that the equilibrium constant is 1.2 times 10 to the negative 5. Okay, that's going to be equal to 2x squared, because plugging in this for this, we got x, and then we're going to subtract that by 0.25 minus 2x. Oh, and then squared. All right, so far so good. You guys good? Okay, so if you guys look at it, it's very, very ugly, and you can see that there's going to be a quadratic coming. So what we want to do is we want to start off, we want to test the 5% rule. Okay, that way we don't have to waste any time. Okay, so if we want to test the 5% rule, what we want to do is we want to assume that the change right here is negligible, so we don't need to worry about it. So we're just going to ignore that. That's what we do when we test the 5% rule. Okay, so from there, bit more manageable. And so I'm going to simplify it. I'm going to skip a couple steps because it is just basic algebra. So you want to square this. You want to multiply both sides by it. And then you want to simplify the right side. So the right side, you should get 4x cubed. And then on the left side, you'll get 7.5 times 10 to the negative 7. And then just solve for x, and you should get about 0.0057 for your x. Okay, something around there. What you get?
I'm saying, yeah, that's about what I.
Oh, okay, for sure. All right, so we want to test the 5%, or we want to double check to make sure it fits the 5% rule. So let's test it. So what we got to do is we got to take x, and we're going to divide it by the initial concentration of your reactant. Okay. Okay, so we're going to do 0.0057. We're going to divide that by 0.25. And if it is under 5% or 0.05, then we should be good. And if you calculate that out, you can double check for me. You should get 0.002. And so that passes the 5% rule. So we don't need to worry about the change because it's so negligible, it doesn't matter if we skip it. Yeah.
So I did for my coefficients, I did this x,
Mm-hmm.
So my x was 0.0114, and that makes the 5% rule 0.0456. So like, what if there's an occasion where like I got something higher?
0.0456.
Yeah.
You're still underneath the 5% rule, so you should be
Like,
fine.
what if it was above the coefficients?
Yeah. So if it's very close to 5, I would still go with just using the 5% rule. Don't do the quadratic if it's really close like that. So if you got like 6%, 7%, I would just still ignore it. Yeah. because at that point it's just rounding issues, so it's not a big deal. Good question though. Any other questions? Okay, so we got our change, and then from here you just need to plug it in, and that will give you your concentrations, because it's asking for the concentrations of all the compounds. So we got to answer what they're looking for. So the concentration of NO2 at equilibrium. Now I know that we use the 5% rule to ignore it, but we don't want to write just 0.25. We do want to show that there is a change. So you just plug it in for x. So 0.25 minus 2 times this value. And then so for nitrogen dioxide, I got 0.2, around 4 molarity. As long as you got something close to that, you should be fine. The concentration for NO at equilibrium, you just want to double it, so 0.0114. And then the concentration of O2 at equilibrium is just going to be x, so 0.0057 molarity. And so this right here will be the final answer. Okay. All right, so I know that was a lot, and I kind of skipped a lot of steps, at least in the calculation. So do you guys have any questions? Or hopefully hasn't been too long since we did it, so. Yes. All righty, everybody good? Pretty comfortable with ice tables? So basically, the key point that we want, the reason why we're going over this is to practice using the ice tables, because we'll be continuing to use them. But also, the thing I do want to point out is that the equilibrium constant is a ratio between the products and the reactants. Okay, that's what's going to be important as we go forward. Okay, so let's talk about why the equilibrium constants are important. Now, you guys don't need to write down this big text in the beginning. I'll I guess simplify it for you guys. So like I said, K is a measure, it's a ratio, and it tells us how the reaction proceeds. So if K is greater than 1, do you guys remember which side dominates, products or reactants? Yeah, products dominate. And I'll write dom. Okay, and then if K is less than 1, that means obviously the reactants will dominate. Okay, so based on the K, you can tell at when the reaction comes to equilibrium, which one you're going to have more of. Okay, if K is larger than 1, more products. It's less than 1, reactants. And depending on how big or how small the numbers are, it tells you how much the products or reactants are going to dominate. Okay. That's so quiet today. Such nerds. Can't stand nerds. All right. Okay, so based on that, so let's talk about why, how we can apply, this knowledge of K and equilibrium. Okay. So the first thing that K allows us to do is it allows us to predict which way the reaction is going to go. Okay. So we have a reaction right here, N2 and H2 to make ammonia. And so if let's say we place these concentrations of these gases in a container, we're basically going to look at how will the mixture react to reach equilibrium. Okay. Whether these two will react to form this, or if this will break down into this. So if we have it, you know how we were looking at the ice table and we had only the reactants in the beginning, right? But now we're going to be looking at systems where we start with both the reactants and the products, and we're able to tell whether or not more products will form or more reactants will form based on the equilibrium constant. Okay. Okay, so what we can do is we can set up the equilibrium constant expression. So if you guys take a look at this, it's just the products on the top divided by the reactants on the bottom. And we can substitute the concentration. So 2 for H2 right here, 1 for N2 down here, and 2 for NH3 here. And that's going to give us 0.5. Okay. Now this value right here we're gonna call this value Q, okay? And Q is basically the ratio of the compounds before equilibrium. Okay, so that's different from K. K is at equilibrium. Okay, so K tells us the ratio when the reaction comes to equilibrium. Q is the ratio while you're still getting there. So Q will always be different for a reaction depending on how much you have for the reactants or the products. K is a constant for each reaction at a specific temperature. Yes. Yeah, so that's another way to think about it. Yeah. Yeah, so Q tells us basically what's going to happen in order to get to equilibrium concentration. Yeah.
But it's like if A is like greater than one, does that mean there's more products or like products are reducing?
So if K is greater than 1, that means at equilibrium, you're going to have more products than you're going to have reactants. Okay. Yeah.
Okay. And then the opposite is true.
Correct. Yeah. Okay, so if we take a look at Q versus K right here, okay? So what we're going to do is we're going to take a look at Q in relationship to K. So right now, is Q greater than K or is it less than K? Yeah, this is greater than K right now. So it's greater than. Okay, so at the beginning of our system, when we put these compounds into a container, basically the ratio of products is greater. Basically, we have too much product. Okay, so that's one way you can think about it. If Q is greater than K, we have too much. Now I'll write P for product. Okay. If Q is greater than K, you have too much product, right? Because again, we're just looking at a ratio. You have more product than you need at equilibrium. Okay. So if you have too much product and the system is trying to go to equilibrium, what's going to happen to the concentration of the reactants? Are you going to get more reactants or are you going to get less reactants? Yeah, it's going to make more reactants. And so reactants, we write them on the left side of the arrow, right? So we say that the reaction, it proceeds to the left. Okay, so we'll write proceeds left. Okay, so it starts making more reactants in order to make the ratio that it wants at equilibrium. Okay. So that's how we predict which way the reaction is going to go. All right. So if Q is greater than K, you got too much product, and so the reaction is gonna proceed left. Okay. And that's basically what all this text is describing. I have it written down here real nicely for you if you want to copy it down, but it'll be available for you right here. If Q is equal to K, obviously it's at equilibrium. Q is greater than K, you have too much product, so you make reactant, and then the opposite is true as well. Yeah. Yes. Yeah, correct. So yeah, this is a constant, and either you'll be able to calculate it or it'll be given. Yeah, good question. Okay, so with that being said, I'll give you guys about 3 or 4 minutes and see if you guys can take this huge wall of text, decipher it, and figure out which way the reaction is gonna go. Okay, so basically what you want to write for your answer right here is just tell me which direction the reaction is gonna go. Is it gonna proceed left? Is it gonna proceed right? Okay, and you got your moles and your volume right here. So take about I'll give you guys 5 minutes to calculate that, see if you guys can figure out which way it's gonna go. And then after that, we will go on to the next part. I'll make this a little bit bigger so it's a little easier to see. Okay, so I set up the equation for Q for you. It's basically the same thing as K. The only difference is that K is at equilibrium and Q is the ratio while it's still getting there, right? So we're gonna plug in our values for high. So high is right here. And so again, you can divide it by 2 liters if you want to find molarity. But it doesn't really matter because at the end of the day, everything is being divided by 2. So the ratio is still going to be the same, regardless of whether you divide by 2 or not. So I'll plug in molarity, just because that's how I did it. But you're going to get 0.01 squared on the top. On the bottom, you're going to get 0.005. And then you're going to get 0.015. Okay. And then you calculate that out, and for Q, you will get a value of 1.33. Okay, something around there. All right, so now we have our value for Q, and since this is not at equilibrium, right? So this is not at equilibrium, K is at equilibrium. What's going to happen is the system wants to get to K. It's going to either make product or reactant so that the ratio gets to where K is. Now, if you take a look at this, our Q is obviously less than the K, right? So let me try to phrase this very carefully so I don't confuse you guys. So at right now, when we have Q, do we have more reactants or more product than we would at equilibrium? Yeah, we have more reactants, right? We have more reactant right now. And that the reason why is because we have a smaller ratio of reactants compared to product than we want at equilibrium. So all right now. Okay, so in order to get to equilibrium, we need to make more what? Yeah, so we need more product. Okay, so if we need more product, which way is the reaction going to proceed? Yeah, we're gonna go right. Man, I should have picked the problem where we go left so I could sing Beyonce. Irreplaceable. So we go left. All right. Make sense? Not too bad? Okay. So for the next problem, we're gonna combine it with an ice table. I know, so much fun. Love math. Love math. Okay. So yeah, I'll show you guys how we can use this with an ice table. So I got my reaction right here. So I'll give you guys about a minute to set up the ice table. Okay. Yeah, equation's right here. I'm gonna set up my ice table as well. So take about a minute to do that. Okay, so we got our ice table. We did the molarity concentrations or calculations. Basically, you just take all the moles and you divide it by 5 liters. Okay. All right, now it tells us the K value. So I'm going to write it up here on the top just so we have it as a reference. The K value is 129. Okay. And it's written right here. 129. All right, now if we take a look at the problem, it's asking us to find the equilibrium concentrations of all the involved compounds. So basically, we just want to figure out what numbers should go in these boxes, right? Tic-tac-toe. Okay. Now, if you guys notice, it's different from the problems that we've been doing before because we have everything up here, right? We start with reactants and products. And so the problem here is we need to figure out what's going to go into change, right? We need to know whether it's positive or negative for the reactants versus the products. Basically, we want to figure out, are we going to make more reactants or are we going to make more products, right? That's why, that's basically what we need to figure out. And that's the problem that is presented when we have concentrations for everything in the beginning.
So is the like specific of the Q important to the problem, or they just if it's less than?
If it's less than or more than.
So you don't have to like put it in.
Yeah, if you can do it in your head, then that's great. Yeah,
Like
you can save the stuff.
actually find the thing and know which way to see the problem.
Yeah, then it's just a regular ice table. So yeah, I'm gonna, like Josie said, we're gonna calculate for Q. So I will give you guys 2 minutes. Is that enough? 2 minutes to calculate what Q is. And then we'll go over how we can use Q in order to figure out how to solve the rest of the problem. Okay, so take about 2 minutes to find Q. Okay, so for your Q value, you should have gotten 6.25. Everybody guys got that? Okay, so our Q value is 6.25. So based on that information, which way is the reaction going to proceed? To the right. Yeah, it's gonna go to the right. I did not think this through. To the left, to the left. Okay, so to the right. Okay, which means we're gonna make more products, right? So when we go to our change column, are we gonna have a positive or negative change on your product side? Exactly, positive, which means you're going to have a negative change for your reactant side. Okay, so from there, it's just the regular ice table problem. Isn't this amazing, guys? I guess not. Thank you for being the only one who responded. I think it's pretty cool. All right, so we got our equilibrium, we got the variables or the equations for our concentrations at equilibrium. And then from there, it's just a regular ice table problem. So we are going to take our K value, which is 129. And then we can basically use this equation again. We're going to take 0.5 plus 2x, and that's going to be squared on the top, divided by 0.2 minus x times 0.2 minus x. Yeah, exactly. Yeah, so good observation, Bailey. So if you guys notice, on the bottom, we got the same two things, right? So all we got to do is square it. And that kind of helps us see an easy way to solve this problem, right? We don't need to use a quadratic. We don't even need to use the 5% rule. All we want to do is find the square root of both sides. Okay, and then that'll give you 129 is equal to 0.5 plus 2x divided by 0.2 minus x. And then from there, it's an easy peasy algebra problem. Yes. Thank you, guys. Appreciate it. All right, so I'll give you guys about 2 minutes to calculate out for x. See if you guys can find x, and then use that to calculate the equilibrium concentrations for all of the involved compound. Okay, so just a little time to practice your algebra skills, and then see if you can plug it into the equilibrium concentrations. Give you guys about 2 minutes. Alrighty, guys. So for this problem, for x, you should get a value of 0.133. Okay. And then you just got to plug in x for all of these guys, and that will give you your equilibrium concentration. So the concentration for H2 and for I2 are going to be the exact same value. So I ran out of space. It's going to be 0.067 molarity. And then for high, okay, it is going to be 0.766 molarity. Okay, so there you go. That is how we can use Q in order to find equilibrium concentrations for, I guess, more complex systems. Any questions about that? Alrighty. Yes.
Can you give us like
Exactly. Yeah. If you have like both sides, basically, if you have all of them with something in there, then that's when you use Q. Yeah, 0. Exactly. Okay, so we are actually going to skip 1.26 or 12.26. Oh. Okay, because, and if you want to do it on your free time, you can, because this is literally everything together. So ice table, Q, quadratic equation, a lot of fun. Okay, so we're going to skip that one just for the sake of time. But again, if you want to, here, I'll give you the answer so you guys can check, at least for X. If you want to write this down and use this as a practice problem, in this problem, X is going to be equal to 0.00066 and then 18 if you want all those numbers. Okay, so this would be a good problem to practice for your exam. Wink, wink. And this is the X value. Okay. And again, this is going to involve everything. Istable, quadratic, and cube. Okay. And again, if you ever want to check your answers for any of these, please let me know. I can give them to you. Anyone still need this? Okie dokes. All right, let's move on. Okay, so the second thing that we can use this information for is a lot of times you have K, but you don't have all the concentrations at equilibrium. Okay. So we'll do this problem as an example. It's a lot more, it sounds a lot more complicated than it seems. But I'm gonna write down the equation right here, just so that we can have it. And I recommend you do that too, just so you have the equation. Okay, now the problem tells us that the K value is 1.45 times 10 to the negative 5, okay, 500 degrees Celsius. Okay, and then for this problem, am I moving too fast?
No.
You guys copying? Okay. For this problem, it tells us the equilibrium concentration or the equilibrium pressures. It tells us at equilibrium, hydrogen's partial pressure is 0.928 atm. And then for nitrogen, it's going to be 0.432 atm. Okay, and this is all at equilibrium. Okay. And then we can use the K value to figure out the concentration of NH3 at equilibrium. Okay, so I'll give you guys about 3 minutes to calculate that out. Guess if you need a little bit of direction, basically we know that the K value is equal to the pressure of the products at equilibrium, and then the pressure of the reactants at equilibrium. And then if we have some of those values, we can basically just solve for the missing variable. Okay, so I'll give you guys about 3 minutes to solve that. We'll go over it and then we'll... Alrighty, guys. So hopefully you guys got this, or hopefully I'm right. But basically all you got to do is plug in the equilibrium pressures for N2 and H2, and then from there it's just working with the exponents and then solving for this variable. If it's easier for you to solve this problem by just changing this with X, you can do that. Just make sure you remember that X is the pressure of NH3. So whatever helps you solve the problem, please use that strategy. But at the end of the day, we're looking for the pressure of ammonia at equilibrium, which is this right here. Okay. Alrighty. Any questions? Easy peasy? I'm glad. No, mi español es muy malo. Estúpido.
Mr. O, you know the language is industry.
Thank you. That's beautiful. That's a beautiful statement. Guys, how do you know I'm not just making this up? It's just elven magic.
You're just making it up.
I'm making all this up as I go. All right. So again, we're going to skip 12.28. It's just another problem where we combine everything together. Okay, so we're going to skip that one. Now we're going to go on to, I think, my favorite thing to say. Okay, so this is French. A French student came up with this principle, and as you guys know, as I just said about my Spanish, my French is also very bad. Okay, so I'm gonna attempt to say it. It's Le Chatellier principle. Okay. Okay, so I don't like speaking French and saying things that make me sound dumb, so I actually sound even dumber by saying Le Chandelier, okay? Which is why there's a picture of a chandelier. So I apologize if you find me very uncultured, but I kind of am. So we're gonna be talking about the Le Chandelier principle, okay? All right, so basically what Le Chandelier's principle tells us, or just is that when you have a system at equilibrium, so let's say for example, and you guys don't need to draw this, okay? We got a container with different compounds in it. And again, you don't need to draw this. Okay, and let's just say it is at equilibrium. Okay, so everything is happy. Okay, the compounds are at equilibrium. There's nothing really going on. The forward and reverse rates are the same. Okay, but something happens. Okay, an outside force comes in and attacks. Okay, I know. Okay, so the outside forces could be, you could add more stuff. Okay, more stuff is a change in concentration. Yeah. Temperature is more energy, yeah. The other thing that could happen, no, you're good. The other thing that could happen is there could be a change in temperature. And that's going to change it as well. Or there can be an increase in pressure or change in pressure. Yeah, so depending on what happens, the system is basically disturbed, right? It's at equilibrium, it's happy, and then it is disturbed. Okay, and basically what Le Chandelier's principle tells us is that if it is disturbed by a change, so I have it written right here if you guys want to take a look at it. If the system at equilibrium is disturbed by a change, the system will shift its equilibrium position to counter the effect of the disturbance. Okay, basically it's going to change its equilibrium point in order to accommodate that disturbance. Okay, so it's like a chandelier. It swings this way, equilibrium is going to swing the other way in order to mitigate that change. So the chandelier actually works. Yeah.
A relationship example?
A relationship?
Yeah. You love your relationship.
I know, right? It's hard with equilibrium. Okay. So let's say a man and a woman who are married, okay? Isn't it the actually whatever? I made her torso too small, sorry.
Oh, I think you made the guy like,
Oh, whatever, dude.
they're breaking gender law.
Hey, I'm colorblind, so as far as I know, it's black and gray. Okay, so a little bit. I can't see. I've told you guys this.
You said you slightly colorblind.
Slightly, I can't see very light red and very like light greens. It's very common on the Y chromosome.
Can you tell that it's pink?
Yes.
So why is the guy picking the girl?
I don't. I just started. I don't know. Like what? It's. Well, I think it's sexist to assume that guys can be pink, can't be pink, or can be pink. You guys are making a big deal about nothing. You know what? You know what? I'm gonna just do it in white so you guys can't even see, okay? All right. So I drew a guy and a girl. Since you guys are on
Oh. Oh no.
okay. Yeah, I know. Boo. I'm becoming politically correct. I know. All right. Okay. So we got a guy and a girl, okay? And they are at equilibrium. Okay, they are happy in their relationship / marriage. Okay, but outside forces are gonna come to attack them. Okay, so for example, there's gonna be another girl. Oh my goodness. And she is gonna come and disturb the equilibrium, okay? She's gonna start to DM the dude. She is gonna start to say hi and give him hugs that he doesn't want. This is bugs. Hugs. Bugs. Yeah. No. So she's gonna start disturbing the equilibrium. And what's gonna happen? Yeah, I know. She's gonna be like, what is going on? Right? She's gonna be upset. And so the guy is going to have to shift the equilibrium position. And so he's going to, if they're married, buy her another ring to overcompensate, to shift in the direction. He is also going to give her flowers in order to say, you are the only one for me. Okay. And then he's gonna, I don't know, he's gonna have to start he's gonna put his IG on private. Okay. In order to prevent this girl from attacking their relationship. So now, yeah, now that he's made those changes, the equilibrium position has shifted. Before, his IG was public, now it's private. Okay, before, he had some more money in his bank account, but he had to buy those flowers. No, because we need to keep the equilibrium position still. No, they have to stay. Yeah, therapy. They can go to therapy too. That's very important. Okay, it's very helpful. What else can they do? I don't know. Yeah, date nights. Okay, vacation. A child can help too. And that's his way of saying, I am committed to only you. I will raise this child with you and I will be the child's father. Exactly. And that's a big shift in the equilibrium. No, because nobody talks to me. Yeah. Oh, of course. Of course. She is the only one for me. I don't talk to nobody. I don't have friends, period. For that reason. All right. Anyway. So, Le Chandelier's principle. Oh, I can't spell. Okay, so like I said, these are the three things that you guys want to keep in mind. You guys don't need to write it down because we're going to be going through them one at a time. But these are the three changes in which, or three ways that chemical equilibrium can be disturbed. You add or remove a reactant, so change in concentration. You change the pressure by changing the volume, or you change the temperature. All right, so what we're going to do is we're going to start with the first one. We're going to start with what happens if you change the reactant or product concentration, okay? All right, and this is the reaction that we're going to be looking at. We use this a lot.
What is this reaction for?
So it's actually a very historic reaction and it changed the world. And I'm going to tell you the story about that later. Okay, so, but first let's talk about what happens with Le Chandelier's principle, okay? Okay, so we got a little chart here for this reaction. So basically what's happening is these guys are at equilibrium, right? You got the equilibrium concentrations for your hydrogen, your ammonia, and your nitrogen. We're going to assume up until this point, it is all at equilibrium. They're happy dandy. It's at the equilibrium or the concentration that it wants to be. But then we add H2. And if we add H2, what's going to happen? The concentration of H2 all of a sudden is going to spike, right? So that means here, let me write it. The concentration of H2 is going to go up because obviously we're adding H2. So what's going to happen is the system is going to react. It's going to swing like a chandelier to the other side in order to compensate. So if you guys notice, as H2 is added, equilibrium concentration goes up, or the concentration goes up. And then what do you guys notice happening? Yeah, it's going to start going down. So what's going to happen is when you add H2, the system is going to react by decreasing H2, which makes sense, right? There was already too much H2, so it's going to use some of that H2 in order to do what? It's going to produce, more of the NH3. And then if you notice, what happens to the N2? Yeah, it goes down. And so if you guys notice, there's a pretty clear pattern to what happens, right? The system is going to shift which direction? To the right. Exactly. So if you add reactant, it's going to shift right. And you guys can probably guess what happens if I added ammonia. What would happen? Which way would it shift? Shift to the left, exactly. What if I added nitrogen? Which way would it shift?
Right.
To the right, exactly. That's pretty much it. If you add reactants, it's going to shift to the product. If you add product, it's going to shift to the reactant.
What if I add products and reactants?
So it depends on how much you add them. Yeah.
You finally asked me that question.
That's a great question. Okay, so let me tell you guys why this is a very important reaction. Okay, so let's talk about let's talk about soil. Okay, because we use soil to grow food.
Whoa,
Yes. Whoa, that's a big word. So you are an apes. Okay. I know that's a lot. Hey, who's better, me or Mr. Jones? This on camera. Mr. Jones, you heard that? Heard what Josie Tyler said. Student ID number. I'm just kidding. No, I'm just playing. Hey, objectively, Jones is better than me in every way possible.
He's a little bit more passionate, but
Yes. Number one, he's nicer. Number two, I think he's taller than me, which automatically makes him a better person in every way possible. I think so too.
you teach more because he doesn't want his kids
Oh,
too much.
well, I don't have kids, so anyway.
Yeah.
Me too. Can't wait to put that kid on a poster. Anyway, so guys, I'm telling you, man, if I need a son, because I need to posterize my son and I want to step over him while he's on the ground. And I want him to remember that moment forever.
Oh, tell us about the nitrogen.
Oh yeah. Yeah, sorry. I was talking about more important things. Anyway, so this chemical reaction changed the world because if you guys know anything about agriculture, right? In order to grow plants, there needs to be nutrients in the soil, right? To help them grow. Does anyone know the element that is very hard to obtain for plants?
Phosphorus.
Not phosphorus.
Nitrogen.
Nitrogen,
It's
yes.
also phosphorus.
It's also phosphorus, but nitrogen is actually more difficult.
Is it
Okay.
actually?
Yes, because most of the nitrogen on Earth, do you guys know where it is?
It's in the air.
It's in the air.
78%.
Wow, you nerd! Wow, you're even giving me numbers. Yeah, it's about 78%. So 78% of the air around us is nitrogen gas, N2. Now, if we look at the chemical composition of N2, if we draw N2, what kind of bond is used to keep N2 together? Yeah, triple bond. That's a lot of energy to break that triple bond. Yeah, so basically plants can't just get nitrogen from the atmosphere and turn it into a usable form for them, okay? And so what has to happen is a lot of times you want ammonia or urea or some type of other nitrogen containing compound in order for plants to be fertilized. That's why if you pee or poo on your plant, it's good because there is urea from your body that is in that pee or poo, and the plants will take it and use it. You know, I don't know actually, maybe. Anyway, so basically the reason why this reaction changed the world is because chemists figured out, hey, we got Le Chandelier's principle, right? If we put hydrogen and nitrogen, just hydrogen and nitrogen in a container, it's going to produce some ammonia, right? And we can use that ammonia to fertilize our plants. But we can actually make more ammonia by forcing more of the reactants into the container. And that'll force the reaction to constantly go through and make more and more ammonia.
But isn't that kind of convoluted because it's just like adding more reactants is obviously just going to make more products.
Mm-hmm. Yes. Yes.
That's kind of how it works, Robbie.
Yeah. So they increase the so basically this principle showed us that we can do this, and then if you take out the ammonia as you're doing this process, because you're decreasing the product, you're taking the reactants, you're just producing more. It's basically using this principle to create more and more ammonia. Okay. And nitrogen gas is very abundant, and hydrogen, we can obtain it pretty readily. Okay, so this was used basically to feed all of Europe, which basically fueled the Industrial Revolution, which is why we got all these factories and things like that. But some very smart people also realized, hey, ammonia is pretty toxic. And then World War I happened. So guess what they did with this reaction? Yeah, they made chemical weapons out of this. So it fed all of Europe, and eventually that technology was used to feed a lot of developing nations, but also killed millions of people in World War I.
Wow.
So the moral of the story is, people are smart, but people are bad. People are horrible. Anyway. Yeah, it's like dynamite. All right, so what are we talking about? Oh, 12.29. So see if you guys can take this principle, Le Chandelier's principle, and I want you guys to answer this question right here, okay? I want you guys to take a second to just answer. Pretend this is your FRQ. I want you guys to write down, why does the concentration of N2 decrease after H2 is added? Okay, so why does the concentration of N2 decrease after H2 is added? Simply put, you need N2 to make NH3. That's pretty much it. You need N2 to react with H2. And so obviously you're going to lose some of that N2 to make NH3. I know. All right. Make sense? Okay, so we are going to end with one last thing. We're going to go over the other effect of the Le Chandelier's principle. So let's talk about the next, the next disturbance that could change a shift in equilibrium, okay? Okay, so this one's also pretty easy. So let's take a look at the chemical reaction right here. If you guys can't see it, I apologize. But basically, You got 2A. Okay, it's a fake chemical, and you got B. Okay. Okay, and it is at equilibrium pressure. Okay, so we're at equilibrium pressure. So it is happy. It's good to go. Okay, so if we make the container smaller and we increase the pressure, okay, now we have more pressure than we did at equilibrium, right? And so what the system is going to try to do, what do you think the system's going to try to do? The system want to increase or decrease the pressure now? Yeah, it wants to decrease the pressure. Okay, so if you take a look at the equation, which side of the equation would have less pressure? Less pressure. The right side, yeah, the side with, sorry, Claudia, you're pointing that way and I'm like left, because that's my left, but that's your right, sorry. Yes, it wants to shift to the product, right? So what's gonna have to happen is, oh, let me explain. Okay, it's gonna shift to the side with fewer moles of gas.
Okay.
Okay, because if you have less gas molecules, you're gonna have less pressure. Okay, that's why. Okay, no problem. Okay, I know. Robbie's dad.
I saw the arrow.
All right, so the opposite is obviously true too. If you decrease the pressure, the system wants to increase the pressure, right? To get it to close to the equilibrium pressure. And so what's going to happen is it's going to create more gas molecules, okay? So when you're looking at pressure, it's a little bit different than concentration. You want to look at the side that has more molecules, okay? Make sense?
Yes.
Actually, I guess we can finish all three of them today. Yes. Yes. Huh? Yes. Okay, so with that being said, Susie really wants to do 12:30, so we'll do 12:30. Okay, so I will give you guys about a minute to do this. Shouldn't be too bad. Again, just answer the question as is and then write a quick justification, okay? Okay, 12:30. So here, if you increase the volume, so we want to think about this system. So if we increase the volume, what happens to the pressure? Yeah, it's going to decrease in pressure. So if the system decreases in pressure, which way does it have to shift in order for the pressure to increase?
Right. Right. Right.
Okay, so it decreased in pressure. So the system wants the pressure to what? Yeah, it wants to go back up. It wants to go the other way, right? It's like a chandelier. It's going to swing the other way. So if pressure has to go up, we need to go to the side with more molecules, right? Okay, so which side has more molecules? The left. So it's going to shift to the left, to the left. Finally got that. I need to change up my example so I can get that earlier. Okay, so yeah, it's going to shift to the left. Okay, so yeah, you make the container bigger, the pressure's going to drop suddenly. The system's like, oh my gosh, no pressure. So it's going to increase the pressure by making more molecules.
So that's like this class.
These
When it's
gas
not
laws are
like, oh no.
It's so
Science is dumb. All right,
For eight,
except for apes.
I-
Okay, let's let's do this next time. So we'll close it up right there.